This explosion triggered a coronal mass ejection, CME, but luckily it wasn't headed toward Earth. As solar cycle 25 peaks, events like this offer crucial insights into behavior and space weather. Watch this video to learn more about this eruption and its significance. The event centered on a solar filament, an extended strand of cooler, dense plasma held in place by magnetic fields above the Sun's surface. These filaments are common features, often appearing as dark lines when viewed in certain wavelengths. However, when they destabilize, the result can be dramatic. This particular filament anchored at the Sun's northeastern edge suddenly erupted. Captured in high resolution by NASA's Solar Dynamics Observatory, the event showed plasma unspooling from the surface in bright arcs, leaving behind a glowing trench of superheated gas. The scale of the eruption was notable. The filament stretched approximately 250,000 miles, equivalent to the distance between Earth and the Moon. When it collapsed, it left behind what appeared to be a channel or canyon of plasma with estimated wall heights reaching up to 12,400 m. The visual effect was striking, especially in extreme ultraviolet images. The cause of the eruption lies in the Sun's magnetic architecture. Over time, it can build up in these loops until the structure becomes unstable. When it snaps, reconnection occurs, a process where field lines break and rapidly reconfigure. This releases vast amounts of energy, which in this case powered the eruption and launched a CME into space. Footage from SOHO and GEO-19 satellites confirmed the CME's trajectory. It was moving outward but not toward Earth. The blast appeared to spread slowly, further minimizing any potential impact. This wasn't a solar flare, a sudden burst of light, but rather a slower moving event rooted in dynamics. It created a visible trench in the Sun's atmosphere and served as a textbook case for observing filament behavior in real time. Filaments like this are valuable indicators of magnetic stress. Their formation, stability, and eruption are all tied to the underlying field configurations. When one erupts, it often reveals weaknesses or imbalances in the loops that hold them aloft. That's why researchers pay close attention not just to the eruptions themselves, but to their structures leading up to them. The July 15 eruption illustrated the magnetic reconnection process clearly. As field lines snapped and reformed, they left a heated imprint in the solar atmosphere. This offered a clean case study of energy transfer in the Sun's corona, a region still not fully understood. Additionally, the coronal mass ejection associated with this event highlights the relationship between disruption and space weather. Although this CME wasn't earthbound, it underscores the importance of tracking such events. Earth-directed CMEs can compress the planet's magnetosphere, disturb satellite operations, degrade GPS accuracy, and in more severe cases, trigger geomagnetic storms. These storms can induce currents in power lines and pipelines, leading to outages or damage. Each filament eruption and CME gives researchers new data to refine their models. Factors like eruption speed, direction, and associated flux are fed into forecasting systems used by agencies like NOAA and ESA. Improved accuracy in these models is critical as global infrastructure grows more reliant on satellite-based services. This eruption also fits into a broader pattern of increasing activity. We are currently in solar cycle 25, which began in 2019 and is expected to reach its peak in 2025 or 2026. The frequency and intensity of events like this are expected to rise over the next year, providing more opportunities, but also more risks. As solar cycle 25 progresses, we're seeing an uptick in filament eruptions, solar flares, and CMEs. Scientists expect this trend to continue through at least 2026. Our monitoring capabilities have improved substantially since the early 2000s. Missions like NASA's Solar Dynamics Observatory and SR-SOHO continue to deliver real-time imagery and magnetic field data. Meanwhile, newer missions like NASA's Punch and Parker Solar Probe are advancing our understanding of how solar material moves through space. Punch, in particular, is designed to image the solar wind in 3D, which can help map the structure of CMEs as they leave the corona. Parker Probe, on the other hand, is flying closer to the Sun than any spacecraft before it, measuring the environment near the corona directly. Together, these missions are laying the foundation for more predictive rather than reactive space weather models. While we now have protocols in place to respond to major events such as rerouting flights, powering down vulnerable satellites, or issuing geomagnetic alerts, prediction remains a challenge. Events like the one on July 15 help fill in gaps. They show how fast filaments destabilize, how plasma propagates, and how surrounding fields evolve. There's also a growing call to develop global weather forecasting systems, similar to what we use for hurricanes and earthquakes. As satellite constellations grow and space travel becomes more routine, accurate forecasting becomes not just helpful, but essential. Finally, solar events like this have an outreach component. High-resolution visualizations engage public interest and provide educational material that explains complex processes in intuitive ways. While not their primary purpose, they serve as effective entry points into deeper scientific understanding.